Hey everybody, welcome back to Mr. A's geometry course. Today we're going over section 5.4, which is all about isosceles and equilateral triangles. Let's get into it. We're going to discuss the equilateral triangle first here, which we've mentioned a little bit about previously. For example, we should already know that all sides and all angles of the equilateral triangle are congruent to each other, equal in measure. So all the sides are going to be the same length. And that can be any number. It could be a small triangle where all three sides are 1 inch long. It could be a giant triangle where all the sides are 3,000 inches long, right? All the sides have to be congruent to each other. All the angles also have to be congruent to each other. And we've learned previously that the sum of all angles in a triangle has to be 180 degrees, which means for an equilateral triangle, if all three angles are the same amount of degrees, then they would each have to measure 60 degrees in that triangle. We're going to be using these simple facts about congruent sides and angles and equilaterals to solve for side lengths or angle measures or variables involving side lengths and angle measures, like this example where we have to solve for x and y, which are placed on the sides of a triangle. This is maybe an important distinction here to note here, that these variables are very clearly written outside of the triangles. There's no arrows pointing in, so these are not angles. These are referring to side lengths here that we're being given. And the reason we know that this is an equilateral triangle is because all of our sides have the same amount of marks on them. The same amount of dashes tell me all these sides are congruent. Since I know that this side is 10 units long, I know all the sides need to be 10 units in length. So this side is just x, therefore x has to be 10, because I know the sides need to be 10 units long. This side is y plus 3, and I know all the sides have to equal 10, so y plus 3 must also equal 10. I can subtract that 3 from both sides and figure out that my y variable is 7 units long. In this example, let's recognize again that this is an equilateral triangle because all three sides have the same amount of dashes that are on it. Notice this time though, the variable given is inside of the triangle. So now we need to know about our angles of equilateral triangles. And again, the fact here is that all the angles are congruent. They have to be the same value. And what helps us is knowing that because they all have to add up to 180 in the triangle, each individual angle in the equilateral has to equal 60 degrees. So that 8y plus 4 must equal 60. If you forget the 60 part of it, you can always just say, okay, I know all the angles need to be congruent, so this is also 8y plus 4, this is also 8y plus 4. That just becomes a very long triangle sum theorem question where we say 8y plus 4 plus 8y plus 4 plus 8y plus 4 equals 180 degrees. This is a lot more simple if you can memorize. If all the angles are congruent in a triangle, each angle has to be 60, because 60 plus 60 plus 60 will give me that 180 degrees. All right, so that's a lot easier of an algebra problem to solve there. 8y plus 4 equals 60. We can subtract that 4 from both sides to get 8y equals 56, and then divide both sides by 8 to get y equals 7. Let's see if you can apply some of these facts on your own here. Go ahead and pause the video and try to solve for the variables x and y here in this example. Let's see how you did. Hopefully your first thought here was recognizing this as an equilateral triangle because all three sides are marked congruent to each other. And then you recognize that the x and y are at angles of this triangle. Maybe that x is a little tricky because it's outside, but we do have this arrow very clearly telling us that this angle inside of our triangle is 2x plus 10. And again, the fact that matters here, all the angles have to be congruent in the equilateral, means they all have to be 60 degrees. So the 2x plus 10 here would have to equal 60 degrees. And we're doing algebra there to solve for x. I would subtract 10 from both sides to get 2x equals 50, then divide both sides by 2 to get x equals 25 degrees. Then we're doing the same thing to solve for y, because again, that's just an angle in an equilateral triangle. It must equal 60 degrees. So 3y plus 3 equals 60. Subtract that 3 from both sides to give me 3y equals 57. Then divide both sides by 3, and y would be 19 degrees in this example. In our next example here, we have to solve for three variables, x, y, and z. I hope you noticed something though here, which is that technically it'd be impossible to find the values of these variables, right? And the reason why is because there's no proof that this triangle can be classified as an equilateral, isosceles, or anything, because I have no marks on my given sides here. And that was my bad. In the instructions, I should have said, this is an equilateral triangle, solve for x, y, and z, right? And so, assuming this is an equilateral triangle, let's start with the z in there. The z is inside the triangle, this is at an angle. And as we've done in our last few examples here, all these angles have to be 60 degrees. So, z plus 5 has to equal 60. If we subtract 5 from both sides, we'll get 55 degrees there for z. Okay, the sides are a little bit more challenging in here because I don't have a length given to me. I don't know that like this is 20, therefore I can set everything equal to 20, right? I have variables on all my sides. That thing that's tricky here is that there's only one y, so I cannot start with y. I'm gonna have to start with the x's. And the reason I can do it is by, again, assuming this is an equilateral, I know these sides would be equal in value, so I can set 3x minus 2 equal to 2x plus 5, which is what I'm going to do to solve for x. 3x minus 2 equals 2x plus 5, and I'll do my algebra here to solve. I'm going to move those two x's to the left by subtracting 2x from both sides. That'll give me x minus 2 equals 5, and then I can add 2 to both sides to solve for x here, which is 7. Now, a mistake that some students will make is getting really excited about solving for a variable and then misusing it in their next step in a problem. For example, some people might now take y minus 3 and set it equal to 7, which would be the incorrect thing to do. We still have not figured out how long the sides of this triangle are, but we can find out now that we know what x is. Since I know x is 7, I could plug it into this side, for example, and figure out how long this side should be, which is what I'm going to do next. So that 3x minus 2, I'm going to substitute the 7 for the x. 3 times 7 is 21. 21 minus 2 gives me 19. So I know this side is 19 units long, and because we're assuming this is an equilateral, if that's 19, this side would be 19 units long. This side would also be 19 units long. So the equation to solve for y would be y minus 3 equals 19. And there we would just add 3 to both sides to determine that y is 22 units long. Next, we're going to be discussing our isosceles triangle, which definitely has more going on for it than the equilateral triangle. There are much more complicated things involved here in this triangle. Much more logic is going to be involved in solving isosceles triangles. So let's learn about it here. We're going to have two sides and two angles congruent to each other in our isosceles triangle. And one thing that will greatly help us is to be identifying those congruent sides and those congruent angles in our isosceles triangles. For example, here's our isosceles with our marks. We can see two sides with the same amount of dashes, two angles with the same amount of arcs. That's two congruent sides, two congruent angles. The positioning of these angles and sides matters a lot for isosceles triangles. And we'll explain that using appropriate names for them. Those congruent sides are referred to as the legs of the isosceles triangle. That non-congruent side, the one that doesn't have any dashes, that's not the same as the other two, is called the base. So that's how we will refer to the sides of our isosceles. We have two legs, those are the sides that are congruent. The base is the side that is not congruent. And just an important note, the base is not always on the bottom. If you flipped this isosceles upside down, the base would be on the top side of the figure. So the base doesn't mean bottom. For the isosceles, it's the side that's not a leg. That is your base. We also need to be able to refer to the angles appropriately. Those congruent angles, notice that they both touch the base. They're both adjacent to the base. We're going to refer to those as base angles. So our base angles are the two angles that are congruent. They're the two angles that include the base, meaning the base is the side that connects those congruent angles. The other angle, the angle that is included in the legs, it's where the legs meet each other, that is called the vertex angle. It's the vertex angle. So it's very important to know these parts. Your congruent sides are the legs, the non-congruent side is the base. The two congruent angles, which are always the angles that touch the base, are called the base angles. That other angle where the legs meet is called the vertex angle. Our knowledge of the parts of the isosceles triangle is going to help us answer questions like this example, where we have variables to solve for the angles of the isosceles triangle. Let me remind you, identifying the parts is extremely important. Remember, those congruent sides with the same amount of dashes are called the legs of the isosceles triangle. So we got leg, leg. This other side is called the base. And the reason it's important to remember this is because the congruent angles are going to be the angles that touch the base. So that y doesn't touch this side down here. It's not adjacent to it. It's these two angles that are my base angles. Remember, we always have two congruent sides of the isosceles along with two congruent angles, which are always those angles that include the base down here. So if that's 55 degrees, this angle must also be 55 degrees. So x is 55, right? From there, we can use a triangle sum theorem to solve for y. Isosceles, like any other triangle, all three angles have to add up to 180 degrees. So my y plus both of my 55s for my base angles have to equal 180 degrees, right? If we combine those 55s, we would get 110 degrees. And if we subtract that 110 from both sides, we're going to get 70 degrees for y. Let's see if you can apply that same logic in this example and solve for the value of x. Go ahead and pause the video, again identifying your legs and your base, and therefore your congruent base angles, and see if that can lead you to the right value for x. Okay, let's see how you did. Again, this really boils down to, do you know your parts for your isosceles triangle? I see two congruent sides, it means I know it's isosceles, and I know those congruent sides are the legs of the triangle. So this is a leg, this is a leg, that means this side down here is the base. And I know the two angles that touch the base are the congruent base angles of the isosceles. Since this angle is 50 degrees, this angle is also 50 degrees. I can now find the value of that vertex angle with a triangle sum theorem. X plus my two 50s have to add up to 180 degrees. Those 50s combine to give me 100, and I can subtract that 100 from both sides to get 80 degrees for x. This example is going to cause us to review a little bit of naming angles and identifying angles. We got to find the measure of angle UST if the measure of angle UTS is 44 degrees. So let's find that 44 degrees first for angle UTS. All right, a lot of people will say, it's right here. Okay, which I get it. If you highlight from UT to S, it can help you identify where the angle is. Just remember that the angle itself is the interior of what I've highlighted here. This is angle UTS. So that is where our 44 degrees would be placed in this example. 44 degrees there. The angle we're attempting to find, angle UST, if I were to highlight that, would be these sides right here. The angle itself, though, is just the interior. It's this. Remember, your middle letter is your vertex, where the angle is located. This is angle UST. It's unknown. I can call it x if I want to. From here, again, it's the parts of our isosceles, knowing where they are, that helps us solve for questions like this. These congruent sides, I know are my legs. That makes this side US over here my base. And I know that my angles that touch the base must be congruent. So because this angle is x, this angle is also x, and I can still do a triangle sum theorem here to solve for the measure of that angle. So adding all three angles together is x plus 44 equals 180, and we can do this algebra here to solve for the value of x. Combining like terms, x plus x gives me 2x's, and then I can move that 44 to the other side of the equal sign by subtracting 44 from both sides. So that'll give me 2x equals 136. And now I can get x alone by dividing both sides by 2, and x would equal 68 degrees. Let's just make sure that we're answering our question thoroughly here, because it asks us for an angle, not for x. However, angle UST is where we assigned our x. So angle UST would be the same measure there of 68 degrees. Great example here to apply our knowledge of the angles of isosceles triangles. I can recognize this as isosceles because of my dashes. I see side AB here is congruent to side BC. Remember, that makes these the legs. So we got leg, leg. That makes this down here the base. And again, we know our base angles are congruent in the isosceles triangle. So because this angle is 52 degrees, that angle must also be 52 degrees. So no real math involved there in knowing that y is 52. It's just knowing the parts of your triangle. Now solving for x, that vertex angle here requires our triangle sum theorem. And this is just a little bit of extra algebra because of the expression. 14x plus 6 plus the 52 from angle A plus the 52 that we know now for angle C must equal 180 degrees in the triangle. And we're off doing our algebra. Got a lot of like terms to combine up here. 6 plus 52 plus 52, that would be 110 degrees equals 180. I can get that 14x alone now by subtracting both sides by 110. That will give me 14x equals 70. And now I can get x by dividing both sides by 14. And x is 5 degrees. Why 52? X is 5. Great example here. Easy to get confused with an exterior angle theorem problem because we have an exterior angle of 135 degrees. We learned back in 5.1 that that angle would be equal to the sum of these two angles here, the non-adjacent angles in the triangle. The issue being, though, that we don't have the measure of this angle over here. However, remember that a lot of these angle pairs that we learned way back at the start of geometry are going to apply here, like this one. And so it's hard for some people to focus on other angles that don't have a variable there. But in order to solve for x, we're gonna have to find that angle first. So what I'm gonna do here is I'm just gonna put a y where that angle is, just for the moment so that we can solve for it. Linear pairs are on lines. They gotta add up to 180 degrees like we have on those straight angles, those straight lines. So y plus 135 has to equal 180. And if I subtract that 135 from both sides, I'm gonna get 45 degrees for that angle, for the y. So now that I know this angle's 45 degrees, now I can apply my knowledge of isosceles triangles. Those are my legs that are congruent. That's my base. Those are my base angles that touch the base. They have to be the same. So because that's 45, this angle has to be 45 degrees. And now I can do triangle sum here to solve for x. So x plus 45 plus 45 equals 180. Those 45s will combine to give me 90. And if I subtract 90 from both sides, I get a good lesson in not believing what my eyes tell me, because for sure that does not look like a right angle, but our numbers are telling me that that is 90 degrees. And it's important to note, a lot of times in geometry, things are not going to be drawn to scale, right? So 90 degrees is the correct answer in this example. Of course, we have to make the algebra a little bit more complex, and we also just have to hammer home this point of knowing the parts of our triangle. This question is asking me to solve for the vertex angle, right? I'm gonna show you how to solve for x first, and then we'll come back to that and make sure that we know how to understand what angle it's asking us for. First, let's identify. It's isosceles, because two of the sides are congruent. BU is congruent to UG. They have the same amount of dashes. Those are the legs. This is a leg, this is a leg. This is the base. Again, our base angles are always congruent. Those two angles that touch the base must be equal in value. So because this is x plus 10, I can also use x plus 10 for this angle, since they need to be the same value. From there, I can do a triangle sum theorem. That triangle sum theorem is just going to take a little bit longer to solve because of the length of these expressions. So we had x plus 10s for our base angles. Those parentheses, by the way, don't matter because we're adding them together. If we were subtracting, that would be a different deal. But because we're adding, those parentheses are not relevant. So x plus 10 plus x plus 10 plus the 3x up top must equal 180 degrees. And then we can do our algebra there to solve. We got like terms here. X plus 3x. That is 5x's. 10 plus 10 is plus 20. I can get that 5x alone now by subtracting both sides by 20. And that gives me 5x equals 160. And now I can get x by itself by, is it x plus 10? Yeah, it was x plus 10. Now I can get x by itself by dividing both sides by 5. And x would be 32 units. Now to solve for the vertex angle, I have to plug that 32 into the appropriate angle here. And remember, the vertex angle is that angle where the legs meet each other. It's the included angle of the legs, meaning the angle between, right? Which is right there. So we're just plugging in that value of 32 for our x up there. So 3 times x, 3 times 32, and 3 times 32 would give me 96 degrees for the measure of that angle. All right, now we're getting into my favorite stuff here. All kinds of triangle madness, right? We have classified triangles here. We have angles, triangle sum theorem, exterior angle theorems can be used. Just pulling together all of our knowledge here to solve a problem like this, where we have to figure out the value of x. All right, so this is another problem where I can't solve for x right away. I'm gonna have to find some of the measures of the missing angles here where there are no variables in order to figure out x. First, let's identify where the angle that's given, the 64 degrees is, it's inside of an isosceles triangle here. Two congruent sides, which are my legs, making this side the base, and I know my base angles have to be congruent to each other. So because this is 64, this angle is also 64 degrees. And there's two routes I can take now to solve for x, all right? I can do the linear pair route, which would be finding this angle here, knowing these two are side by side on a line. They're a linear pair, they have to add up to 180. But that would lead to another calculation that would have to be done later. And there's actually something we can do here which would require only one more equation to solve for x. And that's first gonna require us to look at that other isosceles triangle, this one right here. These are my legs, this is the base, these are the base angles that have to be congruent. So if that's x, then this is x. And then the only equation I would have to do from here is just looking at that 64 outside. And hopefully you can recall here, maybe if I draw it separate, it gives you even more of a refresher here, that I can use now my exterior angle theorem to solve for x. Because I have the 64 as the exterior angle, remember that will always equal the sum of those non-adjacent angles inside of the triangle. So 64 here would equal x plus x, which is just 2 x's. And if I divide both sides by 2, I can solve x being 32 degrees in this example. If I went the linear pair route, let me just show you that really quick. I could absolutely go the linear pair route and find out that this angle is 116 degrees. So those have to be supplementary to each other there. That would still, though, require me to then determine that this angle is also x and then have to do a triangle sum theorem there with the x and the 116 equaling 180. I'd still get the 32 degrees for x in the end. The exterior angle just requires less work. You'll notice in all the examples we did there, we were solving for the angles of isosceles triangles, because questions for the sides of isosceles triangles are rare, all right? But I'm giving you here maybe one of the more complex examples of solving for side length with isosceles triangles. How do we know this is isosceles? Well, we have two congruent angles. And isosceles triangles have two congruent angles. Again, identifying the parts is important. The congruent angles are called our base angles, and they always include the base. They touch the base, that means this side is the base, which means these are the legs, And remember, our legs are our congruent sides of our isosceles triangle. So if we recognize this as isosceles without knowing where the legs are, we might use the wrong two sides in solving for x. Now that I know that these are the legs though, I know those are gonna be the important sides to solve for x. Because our legs are congruent, I can set 8x minus 11 equal to 2x plus 13 in order to solve for x. I'm gonna get my x's on the same side here by subtracting both sides by 2x. Right, subtracting both sides here will give me 6x minus 11 equals 13. Now I can get that 6x alone by adding 11 to both sides. So my 6x equals 24. And then I can get x by dividing both sides by 6. X would equal 4. And again, the challenge in here is knowing what to do with this information. It's not just solving for x, we have to solve for the base of the triangle. Since we've already identified these are the legs, that makes this the base. So we need to plug that 4 in for the x there in that expression. So that's side AB, that's my base there. 5x plus 4, I know now that x is 4. So we got 5 times 4 plus 4. 5 times 4 is 20. 20 plus 4 will give me a side length of 24 units for side AB. Guys, this wraps up our video notes here for isosceles and equilateral triangles. I'll see you in the next one, guys. Bye.